fall. Yeah, so if this talk reminds you of the previous talk, well, that's not a coincidence. So let's start. It's not a secret that proving circuit lower bounds is hard, right? We had some very interesting progress about 40 years ago with some very, very mild lower bounds on circuits. Then we had exponential lower bounds on some restricted classes of circuits like monotone circuits or bounded depth circuits. And well, time went on, and well, this is where we are right now. So since we can't say much about normal circuits, we're going to be talking about monotone circuits. So again, that's circuits with ANDs, ORs, no negations. Good, so turns out we know many things about monotone circuits. So we know lower bounds for some specific functions. For example, the click function, which we just saw, right? We know exponential lower bounds for that. We also know things about the matching function. So for a very long time, we knew super polynomial lower bounds for that function. And well, very recently, turns out that we even have exponential lower bounds for matching. But that's not something that we'll hear today. Of course, another question is, can we get optimal bounds either for one of these functions or maybe for any function, right? As in, can we get exponential of n bounds instead of exponential of n to the some constant? All right, and then we also know some structural results. So for instance, there's the very interesting question of, do negations help? As in, imagine that you've got a function that you can compute with a normal circuit with negations. So a function in P. Now, what happens if you have a monotone circuit trying to compute that function? Right? Of course, the function should be monotone, otherwise you can't compute it. There's nothing to say. But it turns out that there are some monotone functions that are computable with circuits with negations, but are not computable with monotone functions of small size. Then there's also the question of, do few negations help? Some interesting results in that direction. You can also think of the depth of circuits. There are some trade-offs of if you have deeper circuits, then they can be smaller on that. So plenty of things we know about monotone circuits. By the way, so even if one of the reasons we care about monotone circuits is because we want to make progress towards normal circuits, we also care about monotone circuits because we can use them to prove lower bounds in other areas. And one particular area is proof complexity, as in, if you can prove lower bounds for monotone circuits for some function, then turns out that immediately from that, we can get lower bounds on the shortest proof that proves some combinatorial principle. All right, so let's continue then with what we prove. And as I mentioned, we've got the click function. You've got a graph. You want to find out, is there a click? If so, say 1. If not, say 0. There's also the click coloring function, where you've got a graph. If the graph has a click, say 1. If the graph has coloring, say 0. If the graph has neither of those, then whatever. This is a partial function. And we had lower bounds that were up to n to the 1/3, so exponential on n to the 1/3 on this. And we can prove lower bounds that go to n to the exponential of n to the 1/2. Right? And again, if this sounds familiar, yes, that's the same thing that we just saw. Of course, the techniques are completely different, or maybe they aren't. You'll tell me at the end of the talk. What else can we say? We can say things about another function, the co-coloring function. Here, you've got a graph, and you have to say, well, does the graph have a coloring, or does it complement have a coloring? And again, we can get better bounds for this function. And now, using these bounds for this function, turns out we can say things about proof complexity of the bit pigeonhole principle. So this is a combinatorial principle where you say, well, I've got 2 to the L plus 1 strings of length L, and you say, no, they're all different. So that's, of course, impossible because there's too many strings. And so you can prove that that's a contradiction. And now the question is, well, what's the shortest proof that you can find for this principle, given one fixed proof system? In our case, this is going to be the cutting plate proof system. And again, we can get better lower bounds in this case. And by the way, this has also, or similar results have been proven. So there's a slightly worse bound, but for a much more general setting. Paul, you'll correct me here if I say something wrong. Right, that's it. Thank you. Yeah. And finally, I mentioned this question about circuits with negations versus circuits without negations. Well, it turns out that we can prove some better bounds for some function that can be computed with circuits with negations, but cannot be computed with circuits without negations. Right, and again, we're going from 1/6 to 1/3. Good, so that's what we prove. Now, how do we do this? Right, well, there's a couple of techniques for proving circuit lower bounds. One is the one that we just saw, which is the approximation method. And it's this idea that you start with a circuit, you remove a gate, you get a function that's close enough. Keep removing gates, eventually you'll get a constant function, but click is far from constant, so that means that you had to remove many gates to get there. Right, and this idea that you can get similar function by removing gates, that's where you use sunflowers to say that this approximation is possible. Now, another technique to prove circuit lower bounds is to go through communication complexity, and that's what we're going to use. So going from circuits to communication, well, that's called the Kazimir-Wigderson communication problem. And here's the idea. You've got a function, and you're going to make a communication problem out of this. So you have two players, Alice and Bob. You'll give one input to Alice, so an input that evaluates to 1. You'll give Bob an input that evaluates to 0. Now, because this is a monotone function, there's going to be some coordinate that Alice has set to 1, Bob has set to 0. And now their task is to go and find what this coordinate is. So let's just see an example with click. We'll make things clearer. If we've got the click coloring function, then a 1 input, that's a graph that has a click. A 0 input, that's a graph that has a coloring. So we're going to give Alice a graph that has a click. We're going to give Bob a graph that has a coloring. We don't need to give them the click and the coloring, and the players can compute anything that they want. And now they have to communicate and find an edge that is in Alice's graph, but is not in Bob's graph. All right. Now, the connection between this communication problem and circuits is that, well, you can look at the depth of a monotone circuit computing that. So the minimal depth of a circuit computing a function is equivalent to the minimum communication complexity for this problem. Now, what we care about is not depth, but size. But fortunately, the connection also applies to circuit size. So all good here. And in fact, we not only care about formulas, so tree-like circuits, we care about DAG-like circuits. So then we need to use something that's called DAG-like communication, which is a bit technical to define. I'm not going to do that. So it's fine to think about tree-like communication. If you know what DAG-like is, then that's what we need. But if not, things don't change that much. Anyway, so now we've got a communication problem that we have to prove lower bounds for. But that's still a hard task. So we're going to use lifting and reduce that to proving lower bounds for decision trees. Good. So we do that using lifting, which is this technique to. It's this technique to prove communication lower bounds starting from lower bounds in some much simpler model. And again, we're going to have some relation that's going to be our query problem over some variables. We'll take each variable and replace it by the indexing gadget. That means that we're going to give Alice a pointer, we're going to give Bob a string, and the output of the function is just, well, look at the position in the string that is being pointed to, and that's the value of the function. Again, let's see an example. Imagine that we've got the collision relation. But collision is, you've got some variables, say 4 variables, and each variable can take 3 possible values. So of course, there's going to be some pair of variables that have the same value. So the task is to find a pair of variables that have the same value. But there could be more than one. And in our example, well, it's this two. Now, what is the composed problem of this? Well, we've got 4 variables. So we're going to give 4 pointers to Alice. Here they are. And now Bob is going to get 4 strings. So here they are, 4 strings. And now when we put this together, we've got that Alice's pointers point somewhere in Bob's input. And we just go and read the same query problem that we had before. Of course, the players don't know that. But what they have to do is to find now 2 characters in Bob's input that are being pointed to by Alice and that have the same color. All right. Now, it's very easy to see that if we've got this kind of lifted problem and we have a query complexity strategy for the original problem, we can get a communication protocol for the lifted problem. Right? You just every time that you query a variable, then Alice can just send a pointer, Bob sends the value, and they continue doing that. Now, the interesting bit is that something is true in the opposite direction. So if you've got a communication protocol for the lifted problem, you can extract from that a decision tree for the original problem. And again, since we need to do this for DAG-like circuits, we'll have to do this for protocol size and not the normal query complexity, but something that's called decision tree width. This just means that instead of looking at the depth of the decision tree, we're going to look at how many queries we need to store in memory. So we're going to think of a decision tree that can forget values and just think of, okay, how many values do I need to remember? All right. So let's go back to our plan. Now, we wanted to prove lower bounds for click, but click is not a lifted problem. So that's a problem, but well, we can always use a reduction and then use the hardness of the lifted problem to prove hardness for the problem we actually want to prove lower bounds for. So let's go and see that. We'll do a reduction again. So we know that this collision relation composed with indexing, this is hard. So I'm claiming that it's hard. So what we're going to do is we'll assume that we can solve click, and then we'll show that we can solve that problem. So what we'll have then is Alice is going to have these pointers. She's going to build a graph that has a click. Bob's going to have a string or a set of strings. He's going to build a graph that is colorable. Right? And again, let's just see an example. Things will be much more clear in that case. So again, let's say that we've got 4 variables, 3 colors, and our indexing has length 5. So Alice is going to have these 4 pointers, and these are the pointers. She's going to build a click in this fashion. So she'll go, and every pointer that she has, she'll go and look at the graph. She'll mark all of these vertices, and then just build a click among all these vertices. But no more edges in the graph. Then Bob, well, Bob's got these 4 strings. So he'll just go to the graph, and every vertex in the graph is going to color the same color that he has. And then he's going to add edges everywhere that he can, as in if there's 0, 1, he's going to add an edge, 0, 2, he's going to add an edge. But of course, he won't be adding edges between 0 and 0 because he wants the coloring to be valid. So he picks the maximal graph that admits that coloring. All right, yeah, and I'm not drawing the edges because that's too many edges. But now what happens when they find a solution to the click coloring problem? Let's think about that, right? So a solution to the click coloring problem was find an edge that Alice has, but Bob does not have. All right. What did our reduction do? Well, if this edge is in Alice's graph, that means that both its endpoints have pointers. Right? So these 2 pointers, we know that they exist. All right. Then, and this edge is not present in Bob's graph. What's the only reason why an edge might not be in Bob's graph? Well, it must be because these 2 vertices have the same color. But if they had different colors, we would have added an edge. So we then have found 2 characters in Bob's input, both of which are being pointed to by Alice, both of which have the same color. So we found the collision. Right? So then we're using the fact that we can solve click coloring to solve pigeonhole composed with indexing, which we are assuming it's hard. So it better be that our function is hard. Now, some technical detail, it's that we're going to use a sparse version of this problem to get better parameters, where here we're assuming that every character can have all possible colors. What we want to do is to restrict the number of colors that each character can have to only 3. And things can be done, gets a bit messier, but that's fine. All right, now talking about parameters, what are the parameters that we end up getting? I mean, some of the experts might be worried because we're using lifting to prove lower bounds. And well, lifting has a well-deserved reputation for not getting very good parameters, right? Because there's often lots of blow-ups involved and so on. But no, surprisingly, things still work. So the exact theorem that we need to prove is this colorful lifting theorem, which is very, very similar to previous lifting theorems. The only thing that changes is that we have an alphabet size that is not binary. So then with that, well, we need to have a gadget size that's a bit larger, so where the size of the alphabet is going to appear here, and also here in the lower bound, but that's about it. Now, assuming that this is true, here's how we can then put all the pieces together and prove the lower bound. So let's take this collision relation, and it's not too hard to convince yourselves that this width query complexity is C. If you've got k variables with C colors, and you're only remembering C-1 colors, well, then you can make a query, and I'm going to tell you the color that you don't remember, so you will never find that there was a problem. So yeah, this should convince you that query complexity is C. Now we take this relation, compose it with the indexing gadget, and here's where we use this sparsification so that the alphabet size is actually constant and not linear. So we can use a gadget that just has size slightly above the number of colors. And then what happens when we do all these compositions and reductions? Well, we're going to get a lower bound of the form this exponentially in C, while the graph size from the reduction, we just got k number of variables times m size of the gadget. If we pick k to be, say, C+1, then we're going to get this C to the about squared. All right. Now, why did we use this colorful lifting? Why was this important? Well, if we try to do this using, say, a binary alphabet, and you can still do that. You can define this binary pigeonhole principle, where you've got, say, 2 to the L plus 1 strings of length L. You're asserting that all of them are different. And you're trying to find, well, a pair of strings that are equal. But then there's this problem that to certify that, you've got these two strings or each of length L, so you have to do L many comparisons. But you can't just point to two locations and say, yeah, this and this are different. You need to point to all these many locations and say, yeah, all these many locations, all of them are equal. And well, since our reduction is going from edges into this, that means that we'll need to have as many edges roughly as possibilities of choices. And that means that when we do our reduction using the binary setting, the graph is just going to be too large. So things will not work out. It's not as bad as this makes it sound. I mean, you can still get a graph that's about cubed, but we couldn't find a way to do this better unless we use these colors. Right, so last thing, just to give you an idea of how we prove this. So it turns out that the original paper that introduced lifting theorems by Raz and Mackenzie 25 years ago already used this idea of colorful lifting. But that was with fairly bad parameters. Then time passed and lifting theorems were proven in different settings. Parameters were very well improved. And in fact, the best parameters so far come from this paper lifting with sunflowers, where they can get gadgets of this size, n to the 1 plus epsilon. Now, this is in the Boolean setting, and it's almost the same setting that we use. We need to use a slightly different setting that works with something called triangle DAGs, which is yet another version of communication. But that is something that we need so that we can prove this proof complexity result. Anyway, once we've got this lifting with sunflowers, there's not that much that needs to change. So the proof structure is this. You've got these two players communicating, and we're going to be measuring the entropy of all the coordinates in our original function. If there's some coordinate that loses entropy, then we want to query it. But of course, because we are making a query and we don't know what the adversary is going to say, we need to be compatible with all possible answers. Now, this is where we would use the sunflower lemma to say that, yeah, if you've got some coordinate whose entropy is large enough, then all possible choices for that coordinate are still valid. And since now we're working with this larger alphabet, well, we can't use the normal sunflower lemma, so, or at least the sunflower lemma with uniform probability. We need to use this bias probability. But other than this, really, of course, you have to go over the theorem, make sure that the alphabets are replaced wherever they need to be replaced, but things don't change that much. All right, having hand-waved this proof, let's finish. So we've proved this lifting theorem with larger alphabets and used that to prove better lower bounds on some circuit and prove complexity questions. And well, there's this idea that we have sunflowers everywhere. So sunflowers appear in the approximation method. We just saw them in the last talk. We see them here in lifting. And there's all these methods, approximation method, lifting, this bottleneck counting method for proof complexity that are using very similar ideas, but we don't have a formal way to say that they're the same. So maybe there is a way to formally say all of these things are the same. Would be great to see that. And of course, there's the question of, can we prove optimal lower bounds? So both for clique and for any function. And that's it from me. Thank you.